The diameter of the observable universe spans a total of 93 billion light-years across. Within this daunting expanse of starlight and wonder sits the Milky Way galaxy, merely a pinprick of light in comparison. And even smaller still is a humble blue sphere, called Earth, our home. My name is Daniel Danielson, and this is Space Stuff. Wait, Neil, space stuff? Oh, f*** all. Neil, I have to go to the bathroom. I know we have a time limit, Neil, but between risking another hour's rental and paying the cleaning bill... Thank you. Under the clearest of conditions, there are 9,096 stars, visible to the naked eye in the entire sky, but only around 2,000 can be seen from any one spot on Earth. And beyond that, there are uncounted trillions just within the visible universe, awaiting discovery. In the simplest of terms, a star is a glowing ball made of plasma, held together by the forces of gravity. Plasma itself is the fourth phase of matter that your first-grade teacher didn't bother to mention. Sorry, little Johnny, but you have to slow down so the other kids don't feel bad. But that's not fair, little Johnny cries. Well, congratulations, little Johnny. Now there's something else you know about the world the other kids don't. Neil, are you crying?
No.
Do it somewhere else, it's distracting. By the way, I need a refill. The formation of a star begins with a nebula, a dense interstellar molecular cloud perfect for fostering new light. Nebulae form in several different ways, primarily either from pockets of hydrogen only just entering the stellar cycle, or from the commingled gases thrown off of stars during their life cycle. A protostar, a star in its infant stage, forms within a nebula where the plasmatic molecular density is high enough to cause gravitational collapse. If large and flammable enough, the protostar will spend 10 million years coalescing in its childhood stages before puberty arrives in the form of the T Tauri phase, when the plasma is finally hot and cohesive enough to shine as bright as Neil's forehead.
Hi.
Do something, Neil, I dare you. At this phase, the star is bigger and brighter than it will be in adulthood, but far colder. To both these ends, the young ball of fire will spend 100 million years gradually yielding to gravity. The immense pressure will intensify the internal temperature as the protostar enters a dance for balance between gravitic forces pushing in and increasing thermal pressure pushing out. If incoming pressure is greater than outgoing, the star will collapse too quickly to cultivate the heat needed for nuclear fusion. And if outgoing pressure is greater than incoming, then the plasma will explode back into space and eventually dry again. Much like human puberty, this part of a star's life cycle is chaotic and messy, marked in part by facial anomalies and huge explosions of energy in the form of superactive sunspots, powerful stellar storms, and violent X-ray bursts. Good Lord, Neil, you've managed to tie the wonder of space to zits on a teenager's face. This is your worst writing since Gooey Newborn. If the protostar's mass is less than 8/10 our sun's roughly 700 million miles in diameter, the protostar will be too small to make the final collapse and create fusion, leaving a brown dwarf behind. Brown dwarf? Who names these things? Well, no, it's not that it's offensive. It just has a certain unpleasantness about it. Because, Neil, I made a brown dwarf when I took that bathroom break before. Do you understand what I'm saying now? Just me? All right, then. If mass is sufficient, after its long battle, the core temperature finally hits 25 million degrees Fahrenheit, and nuclear fusion begins. At this point, pairs of hydrogen nuclei melt together to form atoms of helium, releasing massive amounts of energy and finally becoming a main sequence star. This phase is marked by the establishment of hydrostatic equilibrium, the point at which each layer of the star reaches perfect balance between incoming and outgoing pressure. The star will spend 90% of its natural life in this phase, continually synthesizing helium and often heavier materials. The core is the hottest part of the star, where most of the pre-nova heavy metal building takes place. As two lighter atoms fuse to form a single heavier one, some redundant subatomic particles are converted into energy. Much of the energy, photons, and heavier elements created in the core travel outward in waves, taking 170,000 years to leave the cooler radiative zone. The radiative zone gives way to the convection zone, an area of heating and cooling just under the visible surface of the sun. Hot material in contact with the tachocline region rises to the top of the convection zone, and as heat continues traveling away from it, that material cools, sinking to make room for hotter rising plasma, and then repeats the cycle. The surface of the sun is called the photosphere because it's the only level of the sun that photons can escape, at least that we can directly observe in the form of sunlight. The sun's atmosphere is composed of the chromosphere, solar transition region, corona, and heliosphere. I was supposed to talk more about them, but Neil is waving at me to hurry it along. Oh, and I think he wanted me to be subtle about it. Well, isn't that a shame? Oh, he wants to have a chat. Fun. He's so angry. The heliosphere is a long comet-shaped bubble of plasma, encompassing everything within and slightly past the Kuiper belt. This bubble is formed by and composed of the plasmatic solar winds continually rushing past at between 700,000 and 1.5 million miles per hour. Like the sun, it also has its own anatomic laundry list, because astronomers basically get paid to look through a telescope and start naming things. Much like a comet, the heliosphere moves fast enough through space to form a bow shock, parting space the way a boat parts the sea. The termination shock is the part of the heliosphere where solar winds begin to slow down as they meet resistance from other cosmic forces. The outermost edge of the heliosphere is called the heliosheath, where the solar winds struggle to carve a path through the plasma between stars. Here, the plasma slows nearly to a halt and piles up, pushing hard against the fierce, interstellar winds coming from all directions. The hard boundary between solar and interstellar winds is the heliopause, the point at which particles flowing outwards are redirected into solar revolutions along the bubble's boundary, and particles headed inwards are redirected to flow around that boundary. On the other side of the heliopause is a wall of plasma varying between 50,000 and 90,000 degrees Fahrenheit, and about 40% denser than the solar plasma on the other side. It's unclear as of yet how interstellar plasma might affect the physics of interstellar travel or what effect the plasma might have on biological organisms traveling through interstellar space. But we do know that solar plasma protects us from damaging interstellar radiation that would otherwise make Earth inhospitable to life. Like Helen. As a special treat, we actually happen to have a sound clip of the plasma outside the heliosphere. What the f*** was that?